When you think about deep space, what comes to mind? Probably the vast, quiet emptiness, right? But here's the thing. That void isn't empty at all. It is absolutely buzzing with a constant storm of high-energy particles. And protecting our astronauts from this invisible threat, well, that's one of the single biggest challenges in all of space exploration. Today, we're going to dig into why that danger might be way, way bigger than the official numbers let on. So let's just ask the big question right up front. How safe is an astronaut really on a mission to the moon or even Mars? You might be surprised to find out that the answer is incredibly complicated, and the data we've been relying on, it might be leaving out some of the most dangerous parts of the whole story. Okay, let's dive right in. To really get a handle on the risk, you first have to understand the enemy. The second an astronaut leaves the protective magnetic bubble of our planet, they are stepping into a seriously hostile radiation environment. So astronauts are dealing with three main flavors of radiation. You've got galactic cosmic rays, or GCRs, which are shot out from distant exploding stars. They're mostly protons, but they also include these things called HZE ions. Think of them as tiny atomic cannonballs that are especially good at tearing through human tissue. Then you've got solar energetic particles, or SEPs, which are violent bursts from our own sun that can cause radiation sickness and fast. And finally, the very first hurdle you have to cross, the Van Allen belts. Think of the Van Allen belts as two giant radioactive donuts wrapped around the Earth, held in place by our magnetic field. And to get to deep space, you have no choice but to fly right through them. The inner belt is just teeming with high-energy protons, and the outer one is swarming with super-fast electrons. The trip through them is quick, but it is intense. Now, you're probably thinking, okay, the solution is easy, right? Just add more shielding to the spacecraft. But what's so fascinating, and frankly a little terrifying, is that in the world of deep space physics, more shielding can sometimes make things much, much worse. And that brings us to this wild process called bremsstrahlung. It literally means breaking radiation. Picture this. One of those high-energy electrons from the outer Van Allen belt slams into the aluminum hull of a spaceship. Bam! It stops dead. But all of its energy has to go somewhere, and where it goes is into a shower of powerful X-rays that blast right into the cabin. So here's the kicker. The very thing you built to protect the astronauts, the hull of their spaceship, can become a source of radiation itself. It stops the particles coming from the outside, sure, but in the process, it creates a brand new and in some ways even more dangerous threat on the inside. The same kind of thing happens with cosmic rays, which can create showers of secondary neutrons. A modern ship, like the Orion capsule, has about 20 grams per square centimeter of shielding. Now, that's a huge improvement over the old Apollo capsules. They had less than half of that. But it's still not nearly enough to stop the most powerful particles out there. Okay, now compare that to the shielding on a spacesuit. It's just 0.25 grams per square centimeter. That's, well, it's basically nothing. Against serious deep space radiation, it offers almost zero protection. An astronaut on a spacewalk is incredibly vulnerable. To really drive this home, experts say that a spacesuit literally offers less protection from some of these particles than a simple sheet of aluminum foil. I mean, let that sink in for a second. The suit is a miracle of life support, but it is absolutely not a radiation shield. But the danger doesn't just come from the radiation itself, or even the weird paradox of shielding. A massive piece of this puzzle is the fact that we might be measuring the threat all wrong in the first place. So here's the problem. Many of the electronic detectors that we fly on missions have an upper limit. They're designed to cap out at around 20 or 27 million electron volts. But we know for a fact that particles in the Van Allen belts can have energies way over 100 million electron volts, so we're essentially blind to the most powerful, most damaging hits. And this quote from an expert just says it all. When they were asked about those particles that fly in above the measurement range, the honest-to-goodness answer was, the short answer is, we don't know for sure. That is a huge gap in our understanding. One of our sources had this perfect analogy. It's like you're building a multi-story parking garage, but your plans assume every single car only weighs 1,000 kilos. The moment a bunch of heavy trucks start rolling in, the whole foundation is at risk of collapsing. By ignoring these higher energy particles, we could be making a catastrophic miscalculation. So how in the world do we get a better picture of what's really going on out there? Well, on the Artemis I mission, NASA sent up a couple of silent astronauts to find out. This is the story of one of them. Her name is Helga. Now, Helga is what's known as a phantom. She's an anatomical model of a female torso, and she is packed with over 10,000 tiny radiation detectors. Her job wasn't just to measure the radiation floating around the cabin, but to measure the actual dose being absorbed by sensitive internal organs like her lungs, her stomach, her spine. So let's take a look at the data Helga sent back. This table shows the absorbed dose for different organs. And at first glance, these numbers look tiny. You see the left lung there? Just 1 milligray from the inner belt. It seems completely trivial, like something you wouldn't even worry about. But that's not the whole story, not even close. To understand the true risk to a human being, you can't just look at one organ in isolation. You have to combine all this data into a single, full-body dose. You do this by applying what are called tissue weighting factors, because some organs, like our lungs, are way more sensitive than others. And then you recalculate to find the total dose in a unit called REMS. And when you do that math for a 12-day mission, just based on the data from Helga's lungs, you get this number, approximately 46 rem. Now, that is not a small number. In fact, it's dramatically, shockingly higher than the official mission estimates. So, what does 46 rem actually mean? Is that a lot? Well, when we put this number into context, the answer is yes, a staggering, almost unbelievable amount. This chart puts the severity into stark perspective. That 46 rem dose from a single 12-day trip to the moon is roughly the same as the radiation dose that evacuees received in the year following the Chernobyl disaster. And look at this. It's alarmingly close to NASA's entire career limit for an astronaut, which is 60 rem. A single short mission could use up nearly all of an astronaut's lifetime allowance. Just to be clear, a dose of 600 rem would be fatal. This is serious stuff. And this brings us right back to where we started. As we're gearing up to send people back to the moon and then on to Mars, this hidden radiation danger presents a monumental challenge. Are we underestimating the risks? And are we truly prepared for the invisible storm that's waiting for us in deep space? If you want to go deeper on this, and I highly recommend you do, you have to check out the incredible source material at skillsef.com. You can also subscribe to their YouTube channel and follow them over on Instagram. Thanks so much for watching.